Quantum computing is a method of creating computers based off of what we've discovered in quantum mechanics, a particularly difficult branch of physics involving subatomic particles. Such subatomic particles, when it comes to quantum computing, come in the form of qubits, which are named after regular bits. They are much more capable of computation than the simple bits, and this is painted through how they are used in computing. The uncertainty factor is what these qubits are programmed to compute. They are programmed for tasks larger than what any regular bit computer may handle, hence them dealing with uncertainty and some of humanity's most complex issues. You'll notice that quantum mechanics is often painted in a scary, inaccurate, or otherwise bad light when it comes to entertainment media. As such, quantum computing, as well as the field of quantum mechanics as a whole, is looked upon fairly poorly by common folk. Even geniuses like Einstein have noticed this study and called it spooky, a study with so much untapped potential beyond comprehension. However, when given the chance, quantum computing can prove to be hundreds to millions of times more powerful than today's computers at what they're made to do. Quantum mechanics is a very complex topic, so let's break it to its tiniest of form, which is what it is. It is a field of study that focuses on ionized atoms moving within the quantum level, the place where it gets its name, if you will. Matter is unimportant at this state, unlike in most physics. Instead of focusing on that, it focuses on the things that make it up. The types of computing that can be provided by these particles, which can output a lot of energy, are unpredictable, as well as far beyond their current reach as of the moment. You will hear these qubits a lot when it specifically comes to quantum computing, and what experts have been able to uncover. These are named after bits in regular computers, the term used when you think about the ones and zeros of the computer realm. Qubits are more powerful versions that consist primarily of some sort of quantum matter. Think a photon, an atom, or a tiny piece of superconductive metal. Qubits are quite powerful, hence the basis for why quantum computing as a whole is considered powerful. However, they are very unpredictable and prone to error, be it from the environment or their own error, as for mostly prototype design.
Now, let's talk about the brief history of quantum computing. So rolling back to the early 20th century, scientists were unraveling the mysteries of quantum mechanics, which is a branch of physics governing the behavior of particles at the atomic and subatomic levels. Simultaneously, the world was witnessing the emergence of computers, initially as calculating machines and later as powerful tools for complex computations. Then during World War II, computers played pivotal roles in cryptography and scientific research, leveraging classical computing principles. Meanwhile, quantum mechanics underpinned crucial developments in nuclear physics, notably contributing to the Manhattan Project. Then, during the 1980s, the intersection of quantum mechanics and computer science began to manifest. Paul Benioff's conceptualization of the quantum Turing machine laid the groundwork for exploring computation through a quantum lens. Concurrently, David Deutsch, a physicist, formulated fundamental ideas in quantum computing, including the development of the Deutsch algorithm, which provided one of the earliest demonstrations of quantum parallelism and marked a significant milestone in quantum algorithm design. Yuri Manin and Richard Feynman also furthered the field's evolution by proposing the concept of quantum-based hardware, suggesting that leveraging quantum phenomena could outperform classical methods in certain computations. Now, during the 1990s, scientists began developing quantum algorithms, or sets of rules for solving problems using quantum computers. These algorithms could potentially solve some problems much faster than regular computers. For example, Peter Shor created algorithms that could crack the codes used to keep information secure on the internet. Experimentalists started building small quantum computers using things like trapped ions and superconductors. These early quantum computers showed that the technology was possible, although in the early stages. Then, the milestone came in 2019 when Google and NASA claimed to achieve quantum supremacy with a 54-qubit quantum processor. This feat marked a significant advancement, albeit with ongoing debates within the scientific community regarding the extent of its implications. Now, despite progress, building fully reliable quantum computers is still a big challenge. These computers can be very sensitive to errors, which makes them tricky to work with. However, researchers are optimistic about the potential of quantum computing and are investing more in it. Now, during the current era, recent breakthroughs offer glimpses of promise. Scientists have successfully entangled individual molecules and developed more efficient error correction methods, bringing practical quantum computing closer to reality. Collaborative efforts between academia, industry, and government agencies are driving quantum research forward, with investments pouring into this transformative technology. As we navigate this evolving landscape, quantum computing remains a captivating journey of exploration and innovation. Its potential to revolutionize fields ranging from cryptography to drug discovery underscores its significance in shaping the future of computing. While the road ahead may be challenging, the allure of quantum computing continues to inspire researchers and technologies worldwide.
Let's now answer the question of how quantum computing works. And the first thing we need to know is its use of qubits and computational algorithms. Quantum computers use qubits to transfer information as opposed to traditional computers which use binary bits. This fundamental factor behind quantum computing's potential for exponentially more processing power is the qubit's capacity to remain in superposition. Many algorithms are used by quantum computers to perform observations and measurements. After the user enters these methods, the computer generates a multidimensional space that houses individual data points and patterns. The next is the reliance on quantum-specific computer infrastructure. And there's three components to make up the majority of a real quantum computer's physical construction. Initially, a traditional computer and its supporting hardware are used to execute programs and communicate commands to the qubits. The second part describes a method for transferring signals to the qubits from the computer. A storage unit for the qubits is the last component. This qubit storage unit must meet specific criteria and standards in order to stabilize the qubits. They may include the vacuum chamber housing or a temperature requirement of almost absolute zero. Lastly, the requirement of physical isolation and cooling mechanisms. It turns out that even the most unstable rock star needs more upkeep than qubits. Error-prone qubits can slip into decoherence or the loss of quantum state due to a variety of straightforward events or circumstances. Operating and measuring qubits are two things that can bring down a quantum computer, which is putting it to use. Qubits will also decohere in response to minute vibrations and temperature changes. For this reason, superconducting circuit computers, the most common approach preferred by Google and IBM, must be maintained at almost absolute zero temperature, and quantum computers must be kept isolated. The key feature that triggers quantum computing is quantum superposition, which allows qubits to exist in multiple states simultaneously. This then enables quantum computers to perform multiple calculations simultaneously, and this process is known as quantum parallelism. Another important principle is quantum entanglement, and this allows qubits to be linked in such a way that the state of one qubit can affect another qubit instantaneously, no matter how far apart they are. Quantum computing has the potential to solve complex problems in a variety of fields, and this includes cryptography, drug discovery, climate modeling, and material science. However, quantum computers are still in their early stages of development, and many technical challenges need to be overcome before they can reach their full potential.
Now let's move on to the implementation of technology. First, we have the IBM Q System 1, the world's first fully integrated quantum computing system that is developed by one of the leading companies in quantum computing, which is IBM. They have also made quantum computing more accessible through its Quantum Experience platform, which allows researchers and developers to run quantum computing experiments and programs from their own computers. Google is another major player in the field of quantum computing, with its Quantum AI team working on developing quantum computing technologies for a wide range of applications. In 2019, Google announced that it had achieved quantum supremacy, a milestone where a quantum computer can perform a calculation that is beyond the capabilities of any classical computer.